Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to explain CFD heat transfer analysis, parametric study and optimization of a condenser heat exchanger using SolidWorks 2022. This is the model. From this opening, we will provide freon at a higher temperature and at a higher pressure. We'll expect the temperature of this freon to be reduced at the end. These are the fins. The fins are made of aluminum. From this side, we will provide air at a specific rate. Air will be passing through these fins to reduce the temperature of freon gas. Right? Okay. For starting this simulation, we need to initiate flow simulation environment, and that will be started with flow simulation here. And finally, from wizard, we need to initiate flow simulation environment, and we're keeping the name of the project as project 2 because we have already done project 1. So default name of the project we're giving as project 2. Next to that, we need to select unit system, and in this case we're considering SI unit, and pressure we're considering as bar, and temperature we'll consider as degree Celsius. Next to that, it is an external analysis, and from physical features we're considering fluid flow with conduction, and gravity will be involved, and the direction of gravity will be y indicated by this green arrow, right? So it will be along y, it is minus 9.81 meter per second square, and along z direction it will be 0. Next to that, gases. So we're considering freon at high temperature, it will be in gaseous phase. Definitely we're considering earth 134a. Excluding that, we need to consider air also. We have considered freon R134a and air as fluids. Next to that, we need to consider materials. The freon containing tubes are made up of copper casing, and the fins are made of aluminum. Initially at this point, we'll consider tubes, which is made up of copper. Next to that, we're considering default roughness parameters, and finally thermodynamic parameters. It is 1.01325 bar, and temperature we're considering as 20 degrees centigrade. And solid parameters also, it will be 20 degrees centigrade. Let us finish this. Now you can see this is the computational domain. We can reduce this volume to reduce computational time. So we can edit this computational domain. You can edit this one from other side also. Let us take the right plane or right view. Done. You can check. Our computational domain is ready. You can have the isometric view of this model, and next to that we need to apply our different fluid subdomains, and before that we need to hide this computational domain. Now we need to apply our fluid subdomains, because from backside we will provide air at a specific velocity, and from these tubes we have to provide freon at a specific rate, high temperature and pressure also. Computational domain, fluid subdomains, insert fluid subdomain, and we're providing from these copper tubes freon at a pressure of 39.7 bar, and temperature will be 100 degrees centigrade. So you can change the pressure, it will be 39.7 bar. At a high pressure we are providing freon 39.7 bar, and temperature will be 100 degrees centigrade. Let us select that location from which we'll provide freon. For selecting that specific location, you can have a segmented view of this model. That will be better for selection. You can cut it from a specific plane and select that specific location from which you will provide freon, right? You can cut it from front plane, grain check. Now you can rotate this one a little bit to have the specific location of this copper pipe, right? This is the location. From here we will provide freon at a specific velocity and a specific temperature and pressure, right? So fluid subdomains, insert fluid subdomain, and it will be freon R134A and we are considering pressure to be very high pressure. It will be 39.7 bar, and temperature will be 100 degrees centigrade, and it will be passing from this copper tube entry. Let us select that location. Now this is the fluid subdomain for our 134A. Run check. Done. And we'll provide air from backside of this one, right, at a specific velocity. You can go back a little bit and provide this air from backside. So to provide air at a specific velocity from backside, we can go back to general settings. That could be provided before also. That will be coming from initial ambient conditions. So air will be passing along this direction. So direction will be z. Along z direction, air will be passing at a velocity of 30 meter per second, right? And we're considering the coordinate system as z. Then check. Then okay. From initial conditions, we have provided air to be passing from backside of these fins, and at a velocity of 30 meter per second, it will be flowing through these fins. And through the fins, we are providing freon at a temperature of 100 degrees centigrade and at a pressure of 39.7 bar, right? So it is done. We can have a complete view of the model. This is the complete model. Next to that, we need to apply materials. Inside solid materials, predefined metals, copper. We can select copper from geometry itself. Copper tube is selected. Green check. So we have provided copper for the tubes, and next to that, you need to provide aluminum for the fins and the side walls, right? So solid materials, inside solid materials, and we'll provide aluminum alloys. It is aluminum 6061, and you can select the different fins and the side plates from the geometry itself. Let us select it from here. Let us select the first one, and with shift button on, you can select the last one. So all the fins and the different plates are selected. These are made up of aluminum 6061, right? Green check. We have provided both the materials. Next, we need to apply boundary conditions, right? For applying boundary conditions, it is always suggested to have a segmented view of this model. So we can cut it from a specific plane. Let us cut it from front plane and select that specific location of the copper tube. Green check. Now we can rotate this one a little bit. Boundary conditions, insert boundary condition, and we need to provide freon or R134A from this location. Select that location, and we'll provide freon at a specific velocity of 0.5 meter per second, and thermodynamic parameters, it will be 100 degrees centigrade, and pressure will be 39.7 bar, right? That is already defined from the fluid subdomains. Green check. Done. And at the exit of copper tubes, it should be atmospheric pressure that to be applied again. Boundary conditions, inside boundary condition, it will be atmospheric pressure at the exit of copper tube. Select, and you can see here pressure is 39.7 bar and temperature is 100 degrees centigrade at the exit of copper tube. So we're considering this one to be environmental pressure at the exit of copper tube. Green check. Done. Boundary condition is applied. Next to that, we have to select some goals, and in this case, a lot of goals may be expected, but we're expecting the temperature at the exit of copper tube. By the same time, maximum minimum temperature of fluid also we're expecting. So we can select some goals, insert surface goals, and it will be average temperature of fluid at the exit of copper tube. Selected. Green check. That is average temperature of freon R134 at the exit of copper tube. Excluding that one, we need to have some other goals. That is, we need to have maximum temperature of fluid and minimum temperature of fluid also inside. So goals, insert global goals, and you need to have minimum and maximum temperature of fluid. Green check. We have selected 3 goals. Now let us run this one. We have already run this one with the same data. So you can see the results from the previous project one. Results are loaded. First of all, we need to see different cut plots of pressure and temperature from specific planes. So cut plots, insert cut plots, and you want to see temperature of fluid through front plane. You can check. Now you can see this from front plane. Let us view the orientation. It will be from front end, and it is better to have an animation of this one. Let us play it. You see how fluid particles are moving from inlet to exit. Instead of temperature, you can see pressure also. Let us see pressure distribution from here itself. You cannot see that much of change in pressure. Pressure remains high. That means through this condenser, high pressure freon we can expect at the exit of copper tubes, but temperature will be reduced, but pressure will be remaining same, right? So we can view this one from right plane also. Cut ports, clear and hide, and we'll see this from right plane. So cut port 1 edit definition, and we'll view this one from right plane. Instead of pressure, I want to see temperature distribution, temperature fluid. Go and check. Done. Now we can see this one in the form of an animation. Let us play. It's clearly evident that at the entry of copper tube, the temperature of freon is very high. It is in the range of 100 degrees centigrade, and at the exit, it's reduced. It is in the range of 41 to 61 degrees centigrade, indicated by green color. It is in the range of 51 to 61 degrees centigrade. To see the dynamics of flow particles, you can make the model completely transparent also. Let us make the model completely transparent to make it visible clearly. So this cut parts 1, let us clear and hide. Now the model is completely transparent. We can view different cut parts of pressure and temperature. We have already seen the cut parts of pressure and temperature. Next to that we will see surface plots, right? So insert surface plots, and we want to see temperature distribution through all the boundaries. So we'll use all faces, and it will be temperature fluid. Green check. You can see here at the different levels, temperature is different. Let us rotate this one a little bit for understanding this one in a better way. You can see here temperature at the outer surface of this copper tube. It is in the range of 80 degrees centigrade, 75 to 80 degrees centigrade, which is indicated by yellow color. And at the exit of copper tube, the color is in the range of 51 to 61 degrees centigrade. And also the fins at which we are having cooling, it is in the lower range. It is in the range of 12 to 22 degrees centigrade. You can see here, which is indicated by this blue color, right? Let us clear and hide this one. Next to that, you want to see the very important one, that is dynamics of flow particles, how fluid particles and also air particles will be moving throughout this condenser heat exchanger. For seeing the dynamics of flow particles, to select the specific locations, we select the segment view of this model. Let us cut it from front end and insert flow trajectories. Instead of 20 numbers, let us make it 200, and particles as you are making 0.205 meter. It will be passing from this inside, and we need to select the outside also. Selected. Excluding this one, we can select some fins. Through these fins also air particles will be moving. Let us select those fins also. We have selected all the fins and also copper tube. Through the fins, air particles will be moving in the front direction, in the direction of Z, a expressive velocity of 30 meter per second. Particle study is already generated. Now you can view this in the form of an animation. Let us rotate this one a little bit. It is better to have an animation of this one. Let us play the flow trajectories. Let us play. It is showing dynamics of flow particles in both ways, from Backside of this one, we are providing air at a velocity of 30 meter per second, and inside these tubes, Freon 134A is passing at a high pressure and high temperature. And at the exit of this Freon tube, at the exit of this copper tube, you can see temperature of Freon is reduced. And to reduce the temperature of Freon at the exit level, you can provide more numbers of fins. In this case, to reduce the simulation time, we have decreased the numbers of fins. We can provide more numbers of fins with less thickness to have better cooling effect. Because more the surface area, better will be cooling. So it is always suggested to have more fins, dense numbers of fins with lesser thickness. In that case, more surface areas will be involved and better cooling will be there. In this case, you can expect the temperature at the exit of this one to be in the range of 60 to 70 degrees centigrade. That much of decrease of front temperature is not visible because we have provided less numbers of fins, and the gap between the fins are more in this case. To have better cooling, we can provide more numbers of fins with less gap in between them, right? So we can view this one from right plane also. Let us orient this one from right side. You can see from right side we are providing air that is being circulated through the fins. You can see from different views. From right view first, this is the view from right side. You can view it from front side also. So from this one we can understand the complete simulation effect. What maybe the temperatures at different zones, we can see it, right? Let us clear and hide this one. Let us clear and hide this one. Flow trajectories. Clear and hide. Next to that, we want to see our goal plots. That means we want to see maximum minimum temperature of fluid. At the same time, we want to see temperature at the exit of this copper tube that we obtained from goal plot. And we want to view these things from Excel. You can transport all this data to Excel. So let us select all the goals, and that can be transferred to Excel. And you can view it from Excel here. First one is average temperature of R134A. You can see initially average temperature of R134A is 100 degrees centigrade, and you can see after 399 numbers of iterations, average temperature at the exit of Freon is 62.84 degrees centigrade. That is at the exit of copper tube, temperature is 62.84 degrees centigrade. We have already told that before. We can reduce the temperature at the exit of copper tube by putting more fins with lesser thickness, because if we are providing more numbers of fins, so surface area will be more. In that case, better cooling will be there, right? To reduce simulation time, we have decreased the numbers of fins, and we have provided the gap between the fins more. That can be reduced to have better cooling. Okay. Next one we can see. Next one is a global goal. It is the maximum temperature of fluid. After 397 numbers of iterations, maximum temperature of fluid is 100 degrees centigrade. And next one you can see the global goal. It is average temperature of fluid. It is 23.04 degrees centigrade. There is the temperature of air inside this fluid domain. And finally you can see the minimum temperature of fluid. After 399 numbers of iterations, minimum temperature of fluid is 12.31 degrees centigrade. Right? These are the data obtained from Excel. This is all about our today's analysis. This is a very simple analysis of a condenser heat exchanger. Instead of stopping it here, we can go for some kind of parametric study. That means we can vary the different input variables. Input variables may be the inlet temperature of Freon, or it may be the inlet velocity of Freon, or you can vary the mass flow rate of Freon also. And with these different input variables, we can see our results. And finally, based on these parametric data or parametric results, we can go for some kind of goal optimization. Okay, thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.